Okay, let's continue. With related rates. So, which we introduced last time, rushed through an example, and now let's do some more examples. That's what we're going to do today, just some more examples on related rates. Look at going through those 6 steps, which I told you can solve any related rates problem, see some potential issues that might pop up, and how we would deal with them. So remember, related rates is the idea that if you have related quantities, then their rates of change are also related. And if you can talk about the relationship between quantities with an equation, you can actually talk about the relationship between their rates of change with an equation, namely the equation you obtain by differentiating the original equation. So, essentially, we know about 2 related quantities, or more, you can have more, and an equation that relates them, and you're given some information. Okay, here's some quantities that have a relationship. We know how fast these are moving, how fast is some other one moving. So a question like that is a typical related rates kind of question. Now once you realize it's a related rates question, as we said, you go through those 6 steps. Pretty much always those 6 steps, pretty much always in this order. A couple of issues that can happen here is that sometimes you skip step 2 if step 4 is given, if your equation is already given for step 4. Sometimes you might get to step 6, realize you have some missing information, and you can go back to step 4 to figure it out. Those are the 2 main issues that you would encounter. Maybe a few other small discrepancies, but overall this is the process that's going to get you through a related rates problem once you know that you're looking at one. And so I just want you to see us applying these 6 steps all the time on some more examples. So we're not going to go through all the examples. In the handout I have 12. Just remember that there's a handout here. It's on the class webpage in case you lose the printout. 12 examples. We're probably going to do maybe 3 more and talk about some issues that can arise here. So we actually did example 1, kind of rushed through it. Let's take it slow with example 2 to make sure we kind of understand what's going on. So step 1 in any related rates problem is to read the problem. Not only do you want to know that it is a related rates problem, but you also want to know what are the rates that we know, what are the values that we know, what is the situation that I can maybe draw a diagram from, etc. You want to really understand the situation fully, pay attention to units and all that, so it's important that you read very carefully. Okay, so 2, after you read, if possible or necessary, you're going to set up a diagram of this situation, and you're going to label it intelligently. So let's go with example 2. Reading that, we see the length of a rectangle is increasing at a rate of 8 centimeters per second. The width is increasing at a rate of 3 centimeters per second. When the length is 20 and the width is 10 centimeters respectively, how fast is the area changing? Okay, so that's another classic related rates problem. You're told about several related quantities here, the length and width of a rectangle, and it's also mentioned the area of the rectangle. You're told the rates of change of the length and width, and you want to find the rate of change of the area. That is a classic related rates problem. Here we're told that it's a rectangle, so the diagram should be pretty obvious. We're going to sketch that rectangle. And we will label the diagram. And the labeling is pretty much as important as a diagram here. I will label this, you can label it whatever at this point since it's not specified. Let's call that L for length and W for width. Now again, as mentioned, we label things that are changing with variables, anything that is not changing with constants. Both the length and width I know are changing, therefore I would describe them by variables, letters. So that would be the diagram, and that is the labeled diagram. The 3rd step. So now we're going to list all our information that we know about the problem, and also the information that we want to figure out. Right? So set our intentions, set our goals here, and really make an account for what we know and what we want. Okay? Now in terms of the rates that we know, we know two things. We know the rate of change of the length, and we know the rate of change of the width. Now what are these? Yeah?
DLDT is 8 centimeters per second, and DWDT is 3 centimeters per second.
Okay. Just want to emphasize here, the signs are important. I'm putting a positive 3 here because we're told that it is increasing. Okay? So the signs are going to be an important thing here. We know these are increasing. So these rates are considered positive. Okay. All right, so that's what we know. Those are the rates we're told. And what do we actually want to find? dAdt. So if I let A be the area, I want to find the rate of change of the area at a certain point when what is going on?
Then length is 20 centimeters and width is 10 centimeters.
Okay. So we've read the problem. Hopefully we've understood the problem. We know it's a related rates and we are gleaning everything about the situation. Diagram comes next. Since they didn't give us an equation to go by, hopefully the diagram here will spark memories from high school geometry. And hopefully you're not getting bad memories. Oh my god, high school geometry. Okay, so this will kind of remind you about the equation which is going to come up in step 4. So that diagram, based on that diagram, you're going to come up with the equation. So that's the step here. And you should remember that the area is length times width. Now once you have that equation, which you come up with mostly based on the diagram here, we now know the 5th step is to differentiate the equation with respect to time. What would the derivative here look like?
dAdt equals dLdtw plus L times dWdt.
Because of the product rule. Okay. I have two functions multiplying each other. L is a function of t, W is a function of t. These are both changing, so they're variables, they're not constants, so the product rule applies here. So when we differentiate with respect to t, pretty much anyone that's not t, we have to multiply by their derivative when differentiating, and that will give us this equation. So the quantities are related by this equation, their rates are related by this equation. And now, this brings us to step 6, which is where we're going to plug in and answer the question. Now, who do we want to find here? Well, now we go back to regain our focus. We want dAdt. We are looking for this guy. And so I don't know that guy, so I would just put that back. And hopefully, once you get to step 6, you'll have all the remaining information that you need. dLdt, yes, we know that. W, yes, we know that. L, yes, we know that. dWdt, we know that. We know everything we need to know. So we simply go and plug those in. dLdt is 8. W is 10. L is 20. And dWdt is 3. So this will be 80 plus 60, which is going to be 140. And this is centimeters squared per second. I don't necessarily care about the units. Units are important for a reason, which we'll talk about, but in the answer, I'm not going to care about units. So again, example 2, still not a crazy example. Going through all the 6 steps in this order, no hiccups, so pretty nice example here. So that should jog your memory about how this whole related rates thing would work. Are there any questions on what we've done so far? Okay, let's do it again. Example 3. Is example 3 the one now? Yes. Let's do example 3, and pretty much every related rates problem will go through this template. I can literally just go through and erase this, and we're literally going to fill in this template again. End up with the problem. Okay. So, step one, read. You're going to read very carefully. A 15-foot ladder is resting against a vertical wall. Suddenly and without warning, Batman starts pulling on the foot of the ladder along the ground, away from the wall, at a rate of 2 feet per second. At what rate is the top of the ladder sliding down the wall when the foot of the ladder is 9 feet from the wall? So, what would you say is the diagram here?
Right.
Yeah?
A right triangle.
It's a right triangle. Is going to be the diagram. So, here's the wall. Vertical wall. Over here would be the ground, and over here is the ladder. Now label this diagram. How would you label this diagram? Yeah.
The bottom would be 9, the hypotenuse would be 15, and the...
No, that's not how we label the diagram. Yes.
The ladder would be 15, the wall would be W, and the ground would be G.
Sure. Let's use X and Y. It doesn't matter. You can use whatever you want. The proper way to label the diagram: label anything that is changing with a variable. Label anything that is not changing with a constant. This is always how you want to label the diagram. You would not label this 9 because it is not always 9. The ladder is moving. Batman is pulling the foot of the ladder away. This distance here is increasing. Okay? Consequently, this distance here will decrease. These guys are changing in length, therefore we label them with variables. The ladder itself is 15 feet. It will always be 15 feet. The ladder is never going to change length. So I label that with 15. I would not label this with a variable because it is not changing. Draw a diagram, label things that are changing that diagram with variables, label anything not changing with constants. That is the rule. Okay. Now, what do we know and what do we want in terms of the variables here? What rate do we know? Yeah.
dxdt.
We know dxdt. What do we know about dxdt?
It's increasing at a rate of 2.
Okay, so it's increasing at a rate of 2, which means there's a plus 2. By the way, what do we actually? That's the only rate we know. Yeah, that was the only rate we were told. What do we want to find?
dy dt.
You want dy dt at what point?
When x equals 9.
When x equals 9. There's going to be an instant where my x hits the value 9. That's the instant I care about. Okay, now, question. What can you tell me about what you expect to happen with this value? Yeah,
It's going to be negative.
it's going to be negative. Why is it going to be negative?
The ladder moves down or away.
Because when this is moving and this is maintaining length, this will be decreasing. So again, by reading the problem very carefully, really understanding the situation enough to draw a picture, you can kind of know sort of where your answer should live. If you end up with a positive answer at the end of this, you know you're wrong. Okay, so things like that all come from reading. Step 1 is super important. I don't really write anything here, but a lot of things need to be considered here. Okay, that you set up the diagram correctly and you kind of have an idea of how things are going to work. Okay, so that's step 3. Moving on to the equation. What equation will we use here? Pythagorean theorem. Now that one should jump to mind. Pythagoras' theorem is what we're going to use here because our picture is that of a right triangle. So my mind immediately goes to 2 sets of formulas, either SOHCAHTOA or Pythagoras' theorem. Those are the 2 main ones. SOHCAHTOA deals with angles, Pythagoras' theorem deals with side lengths. Only side lengths are in play, Pythagoras' theorem is going to be my equation. Now the equation is going to be set up how here? How's this going to look?
X squared plus y squared equals 15 squared.
X squared plus y squared equals 15 squared. This equation comes from the diagram. Had you labeled this a 9 and put a 9 here, now you're messed up. It's very important that you label the diagram correctly. Because once you set up an equation from that diagram, You need to make sure that all the important parts are in play. Another thing to worry about here is let's pretend someone labeled this with a letter, right? Like Z. What would happen is over here you'd have Z squared. Now you're going to go through, you're going to differentiate a bunch of things. Now if you do that correctly, you should end up with a dz dt. Now you come over here, you only have dx dy and no dz. Some people are like, what should I do with that dz dt? You know, a lot of students actually get stuck on things like that. The truth is dz dt is 0 because z is a constant. But you don't put yourself in the position where you have to worry about that. Label it a constant in the first place and avoid the issue of trying to figure out what to do with these extra variables. Okay? So again, everything is very important. Read carefully, label your diagram carefully. Things that change, label with variables. Things that do not change, label with constants. It will prevent headaches down the road. Okay, so that's our equation, Pythagoras' theorem, which seems the obvious choice based on this picture. Now, I erased this next section was to differentiate with respect to time. Okay, differentiating this with respect to time gives us what?
2x dx dt plus 2y
Equals 0. Again, if you label this a variable, you'd have variables over here. What do we do with variables? They don't matter, right? Because it was a constant. Okay. So now, hopefully, we can come over here. We know who we want to find. We want to find the dy dt, this guy. So now we might say, okay, we need to solve for that guy. So we're going to plug in everything we know and solve for that guy. So we can divide both sides by 2, so forget the 2's. X we know should be 9. Dx dt we know should be positive 2. dy dt is what we want to find, so we're not going to know that value. But what is the y? Yeah?
We can use the Pythagorean theorem to solve for y when x equals 9.
Right. So here we ended up with a situation, one of the hiccups I talked about. We get to step 6, but there is some missing information. When you get to this point and something like that happens to you, do not panic, do not freak out. The missing information can be found in step 4. We go back to step 4, solve for the missing information. You know that x squared plus y squared equals 15 squared. This means if x equals 9, you'd have 9 squared plus y squared equals 15 squared. How do you solve for y? What's y? Yeah,
12.
y is 12. How do you know?
225 minus 81. Radical 225 minus 81.
I'm not that smart, so let me do the easier way. I'm not going to square 9 and 15 in my head, forget that. This actually falls in line with a pattern that you guys should remember from geometry as well. Anyone know the pattern? Yeah? It's a 3, 4, 5 triangle, right? Calculus people love to put patterns like this inside of it. It turns out that if you have a right triangle, you know one side is 3, one side is 4, the other side must be 5, vice versa. These are what we call Pythagorean triples. They come together very often. And 3, 4, 5 is a very famous one. What you should notice about these triples is that they work proportionally, right? So if I were to multiply this side by 3, multiply that side by 3, all the sides get multiplied by 3. So if I think of one side as 9, the other side as 15, which clearly I have here, the other side is definitely going to be 12. Which I'm not going to square 15 and 9 to figure that out. I realize, oh, it's a 3, 4, 5 triangle. Right. This is 3 times 3, that's 5 times 3. This guy must be 4 times 3. So my y is actually 12. Now I have all the information at hand. Had a little hiccup there, but we know how to deal with that hiccup because Javon told us how to deal with the hiccup. So now we can go back and we can actually plug in. So we would get our x is equal to 9, dx dt is equal to 2, our y we now know is equal to 12, and our dy dt we don't know. That's actually what we want to find. It equals 0. So we end up with dy dt is equal to minus 9 times 2 over 12. 2 into that goes 6, 3 into that goes 3. So minus 3 over 2. And this is also a length, that's feet per second. So that's your answer. And again, we kind of knew this from the beginning, but you can notice here that that's a negative answer, which makes sense, seems legit. We'd expect this guy to be decreasing, so we expect that answer to be negative. If I get here and I get a positive answer, that's a red flag to me. I made a mistake somewhere. So read carefully so you can properly set up a diagram. This kind of hones you into thinking about the problem in a certain way. You kind of know where the answer is going to lie, what properties it will have. So at any point where you're making a mistake, you're going to know it, right? And because you're reading and setting this up properly, you're not going to have any extra information that you have to worry about because you have enough to worry about. You have 6 steps to get through here, right? Don't need any extra fluff getting in the way. So that's the problem. So as the ladder is being pulled away at 2 feet per second, the top will slide down at minus 3 over 2 feet per second. Any questions on this one? Okay, let's do it again. I was erasing that slide. Maybe I can compress these a little bit. The equation down here. Put this up here. Differentiate with respect to time. Add 6. Okay. So that's going to be our template. Really trying to drive home here that we use the same 6 steps all the time. See a related rates problem in an exam, no confusion should come over you. You should immediately know what you should be doing. First, second, third, fourth, fifth, and sixth. You should be getting into action in 0 time. Okay, let's do problem 7. Let's try problem 7. Okay. So step 1 is to read. So problem 7 is a very typical kind of problem. You usually have even an example like this in the related rates section of a typical calc book. A water tank has the shape of an inverted circular cone. The base is 3. The height is 9 meters. It starts out filled with water, but the water is leaking from the bottom at a rate of 2 meters cubed per minute. And for some odd reason, we want to know how is the radius of the remaining water decreasing when the water radius is 1 meter in length. Find this rate. And here, they actually gave us the equation. We actually know that the equation for the volume of a cone is V equals 1/3 pi r squared h. Now initially seeing that, you might think I can just skip the diagram because there's nothing really to set up. They gave us everything we need. But I'm going to actually still draw the diagram here. You'll realize why we actually need it later. So here's the situation. Step 2. We have a conical tank. It's kind of clean, but it's supposed to be a right cone. Let's start labeling this. How can we label this tank? What's the height?
9.
9. It's always going to be 9. We also know the radius is 3. Now, one part that the problem described is the water inside the tank. Right? So we have some water inside the tank here. And two things were mentioned about the water in the tank. The radius of the water in the tank was mentioned. And the height of the water in the tank is also obviously important. You have h here for the height. And so what would you label this length here? R, right? It is changing, so we label it with a variable. The lower the water level becomes, the smaller that value is going to become. So our radius is decreasing here. What about this length here? The height of the water?
H.
That's going to be h. And again, we label it h because it's decreasing. It's moving, it's changing in length. Okay, so that's our diagram. Let's actually start going through here. What do we know so far? What are the rates we know? Yeah?
dv dt is -2.
How do you know that's dv dt?
Because the water is the volume that they're, like, it's the volume that they're asking for.
Yeah. So for a small second, my earlier class mistakenly thought dh dt was -2. One reason that you know that that was telling you about volume is the units. Notice that it's mentioning 2 meters cubed per minute. Meters cubed is not a unit of length, it is a unit of volume. Therefore here they're telling you about volume. That 2 meters cubed per minute is telling you about a volume. So that's the rate of change of volume. Right now, because the water is leaking out, the volume is decreasing. Therefore I know that that should be a negative sign here, because volume is decreasing. Read. Step 1. I know it seems like a throwaway step. It's not a throwaway step. It's very important that you read and you fully understand the situation. Okay. So the units indicate that they're telling me about volume because they gave me meters cubed. I know the water is leaking out, so the volume is decreasing. That should mean I should put a minus, and that answer should be negative. Okay. Now ultimately I'm going to want the rate of change of the radius, which means, again, from this picture, I kind of know that should also give me a negative answer. So at the end of the day, I should also get a negative answer, and I kind of know that ahead of time. Okay, what do we want? I just mentioned what we want. We actually want the, how the radius is decreasing. So I want to know how dr dt is behaving when, what situation? When r is 1. Okay, so we've read, fully understand the situation, we have a picture to go with the situation, we write down our knowns and what we want, we were given the equation, very nice of them. The next step is to differentiate the equation. So what would the derivative of this be? Derivative of this guy, what is it going to be?
dv dt. Oh wait, no, yeah.
dv dt? Huh?
Like the whole equation, yeah. 1/3 pi 2r times dr dt times
T third pi r dr dt times h.
dh dt. Oh, because of,
You need the product rule.
yeah, h and then plus r squared times dh dt.
Well, 1/3 pi r squared dh dt.
Do we have to do that, or can we just do that because of the equation?
Well, you could leave the 1/3 pi out in front, but you'd still need parentheses around these if you leave it out in front.
Okay. Sorry, I was just thinking that.
there's an issue here. Does anyone notice an issue?
We don't have DHT.
We have no information about DHDT. We have no information about the height. We couldn't even solve for that information even if we wanted to. Well, we could plug in, we'd have to find what the volume is, but we don't even know the volume. So that's actually a problem. So we get here, going through these steps, and we realize this guy starts showing up, and we have no information about that guy. And at this point, you're like, don't lie to us, man. Tom, these stuff don't solve anything. Well, no, that's not what's going on. This situation is salvageable, I promise. Does anyone kind of have an idea of how we would deal with this one?
We can convert H to the R.
Okay, there is probably a way to convert the H's to R's, right? That might be an idea, and that is actually correct. Now, how would that be accomplished? So this isn't a very useful form. They gave us that, we thought they were doing us a favor, but they kind of didn't really give us the best kind of equation to use here. So here is the trick for a problem like this, which is why they like doing it. There's all these geometric tricks that you'd have to remember. But the trick here is to actually take a slice here. Right? So imagine that we've sliced through, taken a planar slice here of half a cone, and then we move that plane outside, right? So you'll notice the image that you have will look like this, right? So you're going to get a triangle that looks like that, where the length across here is R, length across here is 3, the height here is H, and the height here is 9. Now, do you see how we can get H in terms of R? What do you see here? Yeah,
There's similar triangles.
similar triangles. We've just obtained similar triangles. Okay, so what we have here is similar triangles. Okay. So let's see our diagram. Right? And this was kind of my warning on the second page about, yeah, you need to remember all these little intricate facts from geometry. If you want to know all of the ones you have to remember, just do a bunch of problems, go through all these examples. You'll kind of pick up on what you need to remember. Similar triangles, very common trick. 3, 4, 5 triangles, very common trick. Remember Pythagorean theorem, SOHCAHTOA, all those things. Very commonly they'll show up. Now for similar triangles, all we need to do is remember that they are proportional. So the height over the base of the big triangle is going to be equal to the height over the base of the small triangle. And so here, height over base of the big triangle is going to be 9 over 3. Height over base of the small triangle is going to be H over R. And so from this we can conclude that our H is actually 3R. So what we're going to do is going to apply that here. So we're given an equation, wasn't the best form for us. We can actually now rewrite this as 3R. So in other words, our volume for this particular cone is pi r cubed. And so now the variable h is eliminated, so we don't really need to know anything about it. And so it's another situation that can arise. Sometimes your equation does give rise to extra variables through no fault of your own. You did everything right, you labeled everything correctly. Usually when that happens and you know you did everything right because you followed the steps, usually what's going to happen is there's a way to rewrite one of the variables in terms of the other. So you're going to look for some sort of geometric trick to actually do that. At this point you differentiate with respect to t. So this is 3 pi r squared dr dt. So that's the derivative, and at this point, we pretty much have everything we need. So we're just going to plug in. dv dt is minus 2. 3 pi times r, we know is 1. dr dt. And so I can solve for the dr dt here. Get minus 2 over 3 pi. And again, it makes sense from our picture with the decrease in water levels. Right? The radius down here is obviously smaller. It gets smaller as it goes down. And so this, yeah, that kind of makes sense. So seems legit to me. Right? So the actual values might be off, but the sign being correct is an important check to know that that is actually going to work. And so there you go. I think we kind of covered all the mishaps that could happen with these guys, so I would try the rest. On your own. And of course you can see me during office hours or something if you want to talk about them. But yeah, I think we'd stop there. Unless there are any questions moving on about this topic related rates. Probably try them, you might have questions coming from doing these examples. So some good tips there. And I will see you on Friday. We'll look at another topic. I believe linear approximation is what we're doing on Friday. Yes.
What were you told on what
Maybe this weekend we start posting some new stuff. Yeah. And remember in the syllabus there are also practice problems that you can try to practice. If you feel like you want more practice than what you're getting, you can also refer to those. No, I didn't get the last one. You should have your test.